Welcome! In this session, we'll explore problem number 1018, binary prefix divisible by 5. This problem challenges us to work with binary numbers and determine divisibility efficiently. Let's dive in and break it down step by step. In this problem, we are given a binary array called nums, where each element can only be 0 or 1. Our task is to determine, for each index in the array, whether the binary number formed by the prefix of the array up to that index is divisible by 5. The result will be a new array of booleans, where each entry is true if the binary prefix is divisible by 5, and false otherwise. The input consists of the binary array nums, and the output is the boolean array indicating divisibility for each prefix. For example, if nums is 0, 1, 1, we will evaluate the binary prefixes 0, 0, 1, and 0, 11 and determine whether each is divisible by 5. Let's look at some examples to understand this better. In the first example, the input array is nums equals 0, 1, 1. The output is true, false, false. Here's why: the binary number formed by the first element is 0, which is divisible by 5, so the first output is true. The binary number formed by the first two elements is 0, 1, or 1 in decimal, which is not divisible by 5, so the second output is false. Finally, the binary number formed by the first three elements is 0, 11, or 3 in decimal, which is also not divisible by 5, so the third output is false. This example demonstrates how we check each prefix step by step. Now consider another example with a different input. In the second example, the input array is nums equals 1, 1, 1. The output is false, false, false. Let's break it down. The binary number formed by the first element is 1, which is not divisible by 5, so the first output is false. The binary number from the first two elements is 11, or 3 in decimal, which is not divisible by 5, so the second output is also false. Finally, the binary number formed by the first three elements is 111, or 7 in decimal, and again, it is not divisible by 5, so the third output is false. Each prefix is evaluated in the same way. Now let's explore a longer input array to see how this process scales. In the third example, the input array is nums equals 0, 1, 1, 0, 1. The output is true, false, 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 true. Here's the explanation: the binary number formed by the first element is 0, which is divisible by 5, so the first output is true. The binary number formed by the first two elements is 0, 1, or 1 in decimal, which is not divisible by 5, so the second output is false. The binary number from the first three elements is 0, 11, or 3 in decimal, which is also not divisible by 5, so the third output is false. The binary number formed by the first four elements is 0, 1, 1, 0, or 6 in decimal, which is not divisible by 5, so the fourth output is false. Finally, the binary number formed by the first five elements is 0, 1, 1, 0, 1, or 13 in decimal, which is divisible by 5, so the fifth output is true. To solve this problem efficiently, we must account for large input sizes, up to 10^5, and handle edge cases like arrays of only 0s or only 1s. These constraints will shape our approach to designing an optimal solution. Here, we start with the brute force approach, which is a straightforward way to solve the problem by directly constructing the decimal integer represented by each binary prefix. For each index in the array, we take the binary prefix from the start of the array up to that index, convert it to its decimal equivalent, and then check if it's divisible by 5. If it is, we append true to the output list, otherwise, we append false. While this approach is simple to understand, the complexity analysis reveals its inefficiency. Constructing the decimal number for each prefix takes time proportional to the length of the prefix, so for an array of size n, the total time complexity becomes n squared. This is because summing up the time for all prefixes results in a quadratic growth. The repeated conversions for each prefix make this approach impractical for larger arrays, leading us to consider more efficient methods. Now, let's look at the optimized approach, which eliminates the repetitive conversion of binary prefixes into decimal numbers. Instead of reconstructing the full number at each step, we track the remainder of the binary prefix modulo 5. This approach relies on the property that adding a new bit to a binary number is equivalent to left shifting the current number and adding the new bit. Using this insight, we can update the remainder efficiently with the formula, remainder equals the previous remainder multiplied by 2, plus the current bit, all modulo 5. This allows us to maintain only the remainder at each step, avoiding the need for large intermediate computations. The steps are straightforward: initialize the remainder to 0, iterate through the binary array, update the remainder using the formula, and append true to the result list if the remainder is 0, or false otherwise. Once the iteration is complete, we return the result list. This method has a time complexity of O(n), since we process each bit only once, and a space complexity of O(1), as we only store the remainder and the result list. The key to the optimized approach lies in the mathematical property that the modulo operation is distributive over addition and multiplication. This means we can calculate the remainder of a composite operation without fully evaluating the intermediate results. By leveraging this property, we only need to track the remainder modulo 5 as we process each bit, avoiding the need to compute large numbers. With this observation, the optimized approach becomes the clear choice for solving the problem. It combines linear time complexity with constant space usage, making it far more efficient than the brute force method. While the brute force approach is conceptually simple, it's impractical for larger arrays due to its (n²) time complexity. The optimized approach, on the other hand, balances mathematical elegance with computational efficiency, making it the preferred strategy for this problem. By focusing on modular arithmetic and avoiding redundant calculations, we achieve a clean and scalable solution. The problem we're addressing here involves determining whether the binary numbers represented by prefixes of a given binary array are divisible by 5. For example, if the array is 1, 0, 1, we need to check if the prefixes 1, 1, 0, and 1, 0, 1 represent numbers divisible by 5. The task is to return a list of Boolean values indicating divisibility for each prefix. To solve this efficiently, we avoid repeatedly converting binary numbers to their decimal equivalents. Instead, we process each digit of the array one at a time, keeping track of the modulo 5 of the current binary prefix. This approach ensures we perform the computation incrementally without handling large numbers. The solution starts by initializing an empty list result to store Boolean values and a variable current_mod set to 0, which will hold the modulo 5 result of the current binary prefix as we iterate through the array. Once the initialization is complete, we process each digit in the binary array one by one. For a given digit, we update the modulo 5 value of the current binary prefix. The binary number formed by appending a new digit can be expressed as current_binary equals current_binary asterisk 2 plus number. Instead of directly calculating the entire binary number, we update the modulo value as current_mod equals current_mod asterisk 2 plus number, %5. This keeps our computations efficient by only working with the remainder, rather than large binary numbers. After updating the modulo, we check divisibility. If current_mod is 0, it means the binary number represented by the current prefix is divisible by 5, and we append true to the result list. Otherwise, we append false. Once all digits have been processed, the result list, containing the Boolean values for all prefixes, is returned as the output. This algorithm leverages several key insights to achieve efficiency. First, modulo arithmetic allows us to determine divisibility without explicitly calculating large binary numbers. By tracking only the remainder, we avoid unnecessary computations and save on both time and space. Second, appending a digit to a binary number can be expressed as current_binary equals current_binary asterisk 2 plus number. Using modulo arithmetic ensures that this operation scales well, as we only need to update a single remainder value. Third, this approach is significantly optimized compared to a brute force method that would involve repeatedly converting binary prefixes into decimal numbers. By incrementally updating the current_mod variable in constant time, the algorithm avoids expensive operations like string slicing or parsing. Finally, the algorithm is space efficient, requiring only a constant amount of extra space beyond the input array and the result list, making it suitable for large datasets. The algorithm relies on two key data structures. The first is the variable current_mod, which tracks the modulo 5 of the current binary prefix. This variable is updated in constant time for each new digit in the input array. The second is the list result, which stores the Boolean values indicating the divisibility of each prefix. The size of this list matches the length of the input array, as it contains one entry for each prefix. Together, these data structures ensure that the algorithm is both simple and efficient, with minimal overhead in terms of memory usage. Now, looking at the complexity analysis, the algorithm processes each digit in the binary array exactly once. For each digit, the operations multiplication, addition, and modulo are performed in constant time. Therefore, the overall time complexity of the algorithm is O(n), where n is the length of the input array. In terms of space complexity, the algorithm uses O(1) extra space, as it only maintains a single variable current_mod and doesn't require any additional data structures beyond the result list. This makes the algorithm highly efficient in both time and space, even for large input arrays. Several edge cases need to be considered to ensure the algorithm handles all inputs correctly. First, if the input array is empty, the result should naturally be an empty list, as there are no prefixes to evaluate. For arrays with leading zeros, the algorithm handles them correctly, as zeros do not affect the modulo arithmetic. In the case of an array consisting entirely of zeros, every prefix will represent the number 0, which is divisible by 5, so the result will be a list of true values. Finally, for single-digit arrays, the divisibility depends solely on whether the single digit is divisible by 5. These scenarios are all directly addressed by the modulo-based approach, ensuring correctness across a wide range of inputs. To better understand the algorithm, let's go through an example. Consider the input array nums equals 1, 0, 1, 0, 1. We start by initializing current_mod to 0 and the result list is empty. For the first digit, 1, we calculate current_mod equals 0*2 plus 1, %5 equals 1. Since 1 is not divisible by 5, we append false to result. Next, for the digit 0, we compute current_mod equals 1/2 plus 0, %5 equals 2, which is also not divisible, so we append false. For the third digit, 1, the calculation gives current_mod equals 2/2 plus 1, %5 equals 0, indicating divisibility, so we append true. For the fourth digit, 0, we get current_mod equals 0*2 plus 0, %5 equals 0, again divisible, so we append true. Finally, for the last digit, 1, the computation results in current_mod equals 0*2 plus 1, %5 equals 1, which is not divisible, so we append false. After processing all the digits, the final result list is false, false, true, true, false. This output indicates that the third and fourth prefixes of the array represent binary numbers divisible by 5, while the rest do not. The example demonstrates how the algorithm efficiently tracks the modulo value using simple arithmetic, avoiding the need to explicitly calculate the binary numbers. With this approach, we achieve both correctness and efficiency, even for large input arrays. This Python solution efficiently determines whether each binary prefix of the input array nums is divisible by 5. The solution uses a single loop, making it computationally efficient with O(n) time complexity. The function prefixes div by 5 initializes two variables, result, an empty list to store the Boolean results, and current_value, to track the decimal equivalent of the binary prefix modulo 5. The modulo operation is crucial to prevent the number from growing too large and ensures that we only retain information about divisibility by 5. The loop iterates over each binary digit in nums. For each digit, we update the current_value to account for the new binary digit. This is done by shifting the current value left, multiplying by 2, and adding the new digit. To keep the computation efficient, we take modulo 5 after the update. After updating the value, we check whether current_value is divisible by 5, i.e., equals 0. The result of this check is appended to the result list. Finally, the function returns the complete list of Boolean values, where each element corresponds to whether the respective prefix is divisible by 5. This approach efficiently handles large input arrays and avoids unnecessary computations, making it suitable for competitive programming scenarios or real-world applications where performance is critical. This is the Java implementation of LeetCode problem number 1018, binary prefix divisible by 5. The logic mirrors the Python solution, with adjustments for Java syntax, such as type declarations and using the list interface with ArrayList. The program iterates through the binary digits, maintains the current value modulo 5, and appends whether the prefix is divisible by 5 to the result list. This approach efficiently handles the input array while staying within the constraints of the problem. In this example, we are given the binary array 0, 1, 1. The goal is to determine for each prefix of the array whether the binary number formed is divisible by 5. We start by initializing two variables, result, an empty list that will store our Boolean outputs, and current_value, which will keep track of the value of the binary prefix modulo 5. Now, in the first iteration, we process the number 0. The formula, current_value asterisk 2 plus number, %5 calculates the new current_value. Substituting the values, we get 0 asterisk 2 plus 0, %5, which equals 0. Since current_value is 0, we append true to the result. Moving to the second iteration with number equals 1, we calculate 0 asterisk 2 plus 1, %5, which gives 1. As current_value is no longer 0, we append false to the result. In the third iteration with another 1, the calculation 1 by 2 plus 1, %5 results in 3. Again, current_value is not 0, so we append false. The intermediate result is true, false, false, so far. The final output for this example is true, false, false, indicating that only the first prefix is divisible by 5. Now, let's explore another example with the input 1, 0, 1, 0. We begin by initializing result to an empty list and current_value to 0. In the first iteration, the number is 1. Using our formula, 0 asterisk 2 plus 1, %5 evaluates to 1. Since current_value is not 0, we append false to the result. For the second iteration, with number equals 0, we calculate 1 by 2 plus 0, %5, which results in 2. Again, current_value is not 0, so we append another false. The result list now contains false, false. So far, none of the prefixes are divisible by 5. In the third iteration, we process the number 1. The calculation, 2 by 2 plus 1, %5 evaluates to 0, meaning the current prefix is divisible by 5. As a result, we append true to the result. For the fourth and final iteration, with number equals 0, the formula, 0 asterisk 2 plus 0, %5 results in 0 again, so we append another true. This gives us the final result of false, false, true, true. This means that the third and fourth prefixes are divisible by 5, while the first two are not. Now, let's analyze a third example with the input 1, 1, 1, 1. Again, we initialize result as an empty list and current_value as 0. In the first iteration, with number equals 1, the formula, 0 asterisk 2 plus 1, %5 gives 1. Since current_value is not 0, we append false to the result. For the second iteration, processing another 1, we calculate 1 by 2 plus 1, %5, which results in 3. As current_value is still not 0, we append another false. In the third iteration, with yet another 1, the calculation 3 by 2 plus 1, %5 gives 2. Once again, current_value is not 0, so we append false. At this point, the result list contains false, 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 reflecting that none of the first three prefixes are divisible by 5. Finally, in the fourth iteration, we process the last number, 1. Using the formula, 2 by 2 plus 1, %5, we get 0. This indicates that the full prefix is divisible by 5, so we append true to the result. The final output for this example is false, 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 true. This tells us that only the complete prefix is divisible by 5, while all other prefixes are not. By following this step-by-step process, we can handle any binary input array and determine which prefixes are divisible by 5. The time complexity for the given solution is O(n), where n is the length of the input array nums. This is because the algorithm processes each element in the array exactly once, iterating through nums in a single loop. For each iteration, the algorithm updates the current_value by performing a series of constant time operations, multiplying current_value by 2, adding the current element number, and taking the modulo operation with 5. Since all of these are O(1) operations, the cost per iteration is constant. Additionally, appending a Boolean value to the result list is also an O(1) operation. By summing this work across n iterations, the overall time complexity of the solution becomes O(n). Now, combining these observations, the total work done in each iteration remains O(1), and since there are n iterations, the total time complexity of the algorithm is O(n). Moving on to space complexity, the main contributor is the result list, which stores one Boolean value for each element in nums. This means the space required grows linearly with the size of nums, contributing O(n) to the space complexity. Aside from this, the algorithm uses two scalar variables, current_value and number, which require constant space, contributing O(1). Therefore, the space complexity is dominated by the result list, leading to a total space complexity of O(n). Looking at a comparison, a naive or brute force approach would involve constructing the binary prefix as an integer for each position in nums and checking its divisibility by 5. This method would repeatedly convert binary prefixes to decimal, an O(k) operation for a prefix of length k. Summing over all prefixes would result in a time complexity of O(n squared). Additionally, storing all prefixes would increase space usage to O(n squared) in the worst case. In contrast, the optimized solution avoids these inefficiencies by maintaining a running value modulo 5, which eliminates the need for repeated conversions. This reduces the time complexity to O(n) and space complexity to O(n), making it far more efficient. When analyzing best, average, and worst cases, the time complexity is consistently O(n), as the algorithm processes all elements in nums regardless of input characteristics. Finally, we can mathematically verify the big O complexity. Each iteration of the loop performs O(1) work, which includes updating the current_value and appending to the result list. For an input of size n, the loop executes n times, so the total work is O(1) multiplied by n, resulting in O(n). For space complexity, the result list is the dominant factor, as it stores n Boolean values, leading to an overall space usage of O(n). This confirmation aligns with our earlier analysis that the solution is linear in both time and space complexity. When solving this problem, there are several common pitfalls to be aware of. One major mistake is misinterpreting binary prefixes. Instead of treating each prefix as part of an evolving sequence, some may incorrectly process them as standalone numbers, which can lead to inefficiencies and even errors. For example, failing to use modulo arithmetic to incrementally update the number can result in unnecessary computations. Another issue to watch out for is integer overflow, especially in brute force approaches where you directly convert long binary prefixes into decimal integers. This is computationally expensive and can fail for large inputs. Additionally, some solutions overlook the power of modulo properties, which allow you to simplify divisibility checks at each step, making the algorithm much more efficient. Logical errors can also arise from ignoring edge cases, such as arrays containing only zeros or alternating patterns. Finally, it's essential to validate input constraints. For instance, if the binary array length is very large, inefficient solutions can fail to meet performance requirements, so always account for constraints in your approach. Now, let's talk about strategies that can be particularly useful during interviews. Incremental computation is a key technique here. By using modulo arithmetic, you can update the current number efficiently without constructing large integers. For example, the formula current_number asterisk 2 plus a_i %5 allows you to process each binary digit incrementally. Another important insight is recognizing patterns in binary numbers divisible by 5. While you don't need to rely solely on these patterns, understanding them can help you optimize your solution and make quicker decisions under time pressure. If you're asked to optimize your approach, consider discussing advanced ideas like using state transitions to manage modular arithmetic, which demonstrates a deeper understanding of the problem. Lastly, it's crucial to show edge case awareness in an interview setting. Be proactive about discussing examples like empty arrays, arrays full of zeros, or arrays with alternating values. This not only strengthens your solution but also reflects your thoroughness to the interviewer. This problem is directly related to other challenges that test similar skills. For instance, LeetCode 1018, which we're discussing, is a foundational problem for understanding binary prefixes and modular arithmetic. Beyond that, problems like LeetCode 1029, two-city scheduling, emphasize optimization and careful decision-making, skills that are transferable here. LeetCode 366, find leaves of binary tree, involves incremental processing, similar to how modular arithmetic is applied step by step in this problem. Lastly, LeetCode 1047, remove all adjacent duplicates in string, highlights the importance of efficient string manipulation, another area where careful updates and optimizations play a role. Exploring these problems can deepen your understanding of different aspects of computational efficiency and problem-solving techniques. Finally, let's look at some alternative approaches to solving this problem. The brute force method involves constructing the binary prefix for each index and checking divisibility directly. While this approach is straightforward to implement, it's highly inefficient for large inputs and risks integer overflow. A more efficient method is to use modulo arithmetic, where you iteratively update the current number with the formula current_number asterisk 2 plus a_i, %5. This approach has a time complexity of O(n) and avoids the pitfalls of large number construction, but it requires a solid understanding of modular arithmetic. Another advanced approach is to model the problem as a state machine, where transitions are determined by the binary input. While this method can provide valuable insights into modular arithmetic problems, it's more complex to implement and may not always be necessary. Each of these approaches has its trade-offs, so it's essential to choose the one that best balances simplicity and efficiency for the problem at hand. Great job! To wrap up, we reviewed the problem, key concepts, and optimal approaches. Remember, mastering binary operations and modular arithmetic is a valuable skill. Thanks for tuning in, and we'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!